2 a.m. Slack's on fire. Your CI pipeline is red across the board. A single Claude code agent has been grinding through a 40-file Slayer refactor for the past 3 hours, and it just hit a context window limit at file 31. The agent has no memory of what it changed in files 1 through 20. The build is broken. There is no rollback plan, and your on-call engineer is staring at a diff that is 4,000 lines long with coherent structure. I have been in that exact room. Not as a spectator, as the architect who signed off on let's just run one agent and see how far it gets. That decision cost us 6 hours of incident response and a full rollback to the previous release tag. Here is the brutal truth no one tells you in the Claude Code Quick Start docs. A single agent hitting a complex codebase is not a productivity multiplier, it is a time bomb. The context window is not a minor technical footnote. It is the hard ceiling of everything a single agent can reason about simultaneously. Once you overflow it, the agent starts hallucinating consistency. It forgets the interface contract it defined in file 3 when it is writing the implementation in file 28. And by the time you notice, the damage is already distributed across dozens of files. The failure mode is not a crash, it is silent semantic drift. That is the hardest kind of bug to debug. So before we talk about patterns and architecture, I want you to feel the weight of this problem. Because the 3 patterns I am going to show you in this lecture exist precisely to prevent this 2 a.m. scenario. By the end of this lecture, you will have a decision framework that tells you exactly which pattern to reach for before you ever kick off an agent run. Now let me flip the picture entirely. Stripe, one of the most complex financial infrastructure codebases. Last year they published an internal benchmark that stopped a lot of senior engineers in their tracks. 1,300 merged pull requests per week, driven by AI agents. Not generated, not proposed, merged. That number is not about raw code generation speed. GPT-4 class models have been fast enough for over a year. The real unlock was orchestration design. Stripe did not point a single powerful agent at their monolith and say go. They decomposed the work. They defined agent roles. They built coordination layers. They treated the problem the same way a staff engineer treats a large project. Break it into scoped units of work, assign ownership, define handoff contracts, and integrate with verification gates. Here is the mindset shift I want to plant right now. And I mean this from 25 years of watching developers hit ceilings. Your job is no longer to write the best code. Your job is to design the system that produces the best code. You are not the musician anymore. You are the conductor. The orchestra can play faster than any single musician, but only if someone is managing the tempo, the key, and the transitions. Without orchestration, you do not get a symphony. You get noise. And that is exactly what a single overloaded agent produces at scale. Expensive, slow, incoherent noise. The bottleneck in AI-assisted engineering has moved. It is no longer can the model generate code? It is can you design the agent system that coordinates the generation? That is the skill gap this lecture closes. But here is what most developers get wrong when they first build multi-agent systems. And it is a mistake I made myself before I found the pattern that actually works. Let me show you exactly what we are going to build together over the next 5 chapters, because I want you to have the map before we start the journey. There are 3 orchestration patterns that cover roughly 25% of the multi-agent coding scenarios you will encounter in real production engineering. I have seen teams reach for the wrong one repeatedly, burnings of agent cost and developer time before figuring out what I am about to give you for free right now. Pattern 1. This is the delegation primitive. 1 orchestrator, 1 worker, 1 scope task. Think of it as the function call of multi-agent design, simple, composable, and the building block for everything else. The engineering principle it maps to, single responsibility. You already know this principle from Solid. You have just never applied it to agent design before. Pattern 2, agent team. This is parallel execution with shared context. Multiple specialized agents running concurrently, each owning a lane of work, coordinated by a lightweight supervisor. The engineering principle here is separation of concerns, the same reason you do not put your database logic inside your React components. Pattern 3, hierarchical delegation. This is the enterprise pattern, a top-level orchestrator that spawns mid-level coordinators that each manage their own subagent pools. The engineering principle is divide and conquer. The same algorithm your merge sort runs on, now applied codebase with hundreds of touchpoints. What I want you to notice is none of these patterns are new concepts. You have been applying their underlying principles for years. The insight, and this is the thing that changed how I run my teams, is that the same structural thinking that makes software systems scalable also makes agent systems scalable. But knowing the patterns is only half the battle. The other half is knowing when not to use each one, and that is where most developers crash. Stay with me, because the next scene shows you the exact decision tool I use before every agent architecture review. Now here is the artifact that ties everything together, and I am going to show you a preview of it now, so it anchors every chapter you watch from here. In Chapter 5, we build the full pattern selection decision flowchart. But let me walk you through the skeleton right now, because it will reframe how you watch every chapter in between. The flowchart starts with one question. How many independent concern boundaries does your task cross? If the answer is 1, you have a single, well-scoped unit of work. You reach for sub-agent. Full stop. Do not over-engineer it. If the answer is 2 to 4, your task touches multiple separable domains that can be worked in parallel. Agent team is your pattern. If the answer is 5 or more, or if your task has dynamic scope that expands as agents discover more context, hierarchical delegation is the only pattern that will not collapse under its own coordination overhead. The second axis on the flowchart is cost sensitivity. Hierarchical systems run more agent calls, which means higher token cost. I have seen teams blow their monthly AI budget in a week because they used a hierarchical pattern on a task that a sub-agent could have handled in 10 minutes. And the third axis is failure tolerance. How bad is it if one agent produces wrong output? In a sub-agent pattern, one failure means one rollback. In a poorly designed agent team with no verification gates, one bad agent can corrupt shared state and cause a cascade. I built this flowchart after watching my teams make the same 3 mistakes in the same order on every new project where we introduced multi-agent workflows. By the end of this lecture, that flowchart is yours, and it will be the single most useful artifact you can bring to your next architecture review. Next chapter, we go deeper. Why single-agent thinking does not just slow you down at scale, it actively breaks the guarantees your system depends on. Let me be blunt. I've watched teams deploy a single agent against a 50-file refactor and wonder why the output degrades after the first 10 files. This is not a prompt engineering problem. This is a physics problem. Every LLM has a context, a hard ceiling on how much information it can hold in active attention at once. When you pile a large codebase, instructions, tool call results, and error logs into one agent, you are not just filling memory, you are diluting attention. The model starts forgetting what it decided 3,000 tokens ago. And here is the part that kills production systems: task coupling. When requirements analysis, code generation, test writing, and documentation all live inside one agent, a failure in any one of those tasks contaminates the entire context. It is the same reason we stopped writing 10,000-line monolith classes in 2005. High coupling, low cohesion. The architecture lesson did not change, only the runtime did. So before we talk about patterns, you need to internalize this. A monolithic agent is a monolithic application, and you already know what happens to those. What you might not know yet is exactly how fast the degradation curve drops, and that number is going to surprise you. Now let me show you the failure mode side by side, because this is where the intuition usually breaks down. When a single agent hits an error, say a tool call returns an unexpected schema, it has 2 bad options: retry with the full accumulated context, burning more tokens and potentially looping, or abort the entire task and give you nothing. There is no clean recovery boundary. The error propagates backward through every decision that was coupled to it. Compare that to a distributed agent setup. The sub-agent handling the schema validation fails. Its orchestrator catches the signal, isolates the failed subtask, retries only that unit, and the other agents keep running in parallel, completely unaffected. This is not magic. This is exactly the same reason we put circuit breakers in microservices. Error isolation is not a nice-to-have. It is the first design principle of orchestration. I have seen teams lose 3 hours of compute cost because one agent got stuck in a retry loop on a malformed JSON response, and the whole pipeline was waiting on it. In a properly isolated setup, that failure costs you 30 seconds and 1 retry. The math is not subtle. But here is the part most developers miss: isolation alone is not enough. Let me make the economic argument concrete. Because abstract architecture debates die in sprint planning meetings, cost numbers do not. Here is a real cost pattern I have measured. Take a task that requires 5 distinct subtasks: requirements parsing, code generation, test writing, documentation, and review. Run it through a single overloaded agent. By the time you hit the 3rd subtask, the context is bloated. Output quality drops. You reprompt. That reprompt carries the entire accumulated context again. You are paying for tokens you already processed. On average, a single agent on a complex task reprompts 2 to 3 times. Your effective token cost is 2 to 3 times your baseline estimate. Now distribute those 5 subtasks to focused agents with clean, minimal context per agent. Each agent sees only what it needs. No reprompting from context confusion. Your total token spend drops 40 to 60% on equivalent tasks. I have run this comparison on internal tooling, and the number holds. The hidden cost of a monolithic agent is not just latency, it is the compounding tax of redundant context on every retry. Now that we understand the problem from three angles, attention, error propagation, and cost, let me show you that you already have all the mental models you need to solve it. Here is the most underrated insight in multi-agent architecture. You already know how to solve this problem. You solved a version of it in software engineering. Divide and conquer is not a new idea. It is what we do when a monolith gets too large to reason about. We split it. The subagent pattern is exactly this. One orchestrator breaks a large task into independent subtasks and spawns focused agents for each. Separation of concerns, the principle that each module should own exactly one responsibility, maps directly to the agent team pattern. Each specialist list agent handles one domain. One agent writes code, one writes tests, one handles documentation. They do not share context pollution. And hierarchical delegation, the idea that complex systems need multiple layers of authority and responsibility, that is the delegation pattern. Senior agents make strategic decisions and pass execution contracts to junior agents. I have been using these exact mental models to structure engineering teams for 15 years. When I first looked at Addy Osmani's taxonomy of agent patterns, my reaction was not "this is new." It was "this is the org chart problem, solved in software." If you've ever decomposed a system into services, you already have the instinct. What you need now is the vocabulary to apply it precisely. And that vocabulary is what we build next. Now let me give you the formal vocabulary, because imprecise language is how teams end up building the wrong thing. Addy Osmani's taxonomy gives us 4 distinct roles, and if you conflate them in design discussions, you will ship the wrong architecture every time. First, the orchestrator. This agent does not write code. It does not call tools directly. It decomposes tasks, issues instructions to other agents, and synthesizes results. Think of it as the tech lean. It plans, it delegates, it reviews. Second, the subagent. This agent receives a bounded task from the orchestrator, executes it with a focused context, and returns a result. Does not need to know about any other agent's work. Third, the specialist agent. This is a subagent with a declared domain expertise, a code review agent, a security scanning agent, a documentation agent. It's preloaded with domain-specific knowledge. Fourth, the delegator. This is an orchestrator that itself operates under a higher-level orchestrator, enabling the hierarchical delegation pattern for genuinely complex pipelines. I want you to use these terms exactly. When you say agent in a design review from this point forward, specify which tier you mean. That discipline alone will save you 3 rounds of architectural rework. And now that we share a vocabulary, we need to talk about how to know, right now, today, whether your existing setup is already broken. Let me give you the diagnostic checklist I actually use in team reviews. You do not need a benchmark suite to know your agent setup is in trouble. 5 symptoms tell the story. Long wait times that keep increasing as your codebase grows, not a network problem, a context problem. Second, repeated context resets, where you have to manually wipe state and restart because the agent forgot prior decisions. If your team has a ritual of clearing context every few tasks, that ritual is a symptom. Third, inconsistent output quality. The same prompt returns production-grade output on Tuesday and garbage on Thursday. This is attention dilution in action. The context load was different. Cost spikes that do not correlate with feature complexity. You are paying the reprompt tax and you do not know it yet. Test failure clustering. Tests fail in unpredictable combinations because the agent made globally inconsistent decisions when coupling its subtasks. I have walked into 3 different teams in the last 2 years and found 4 of these 5 symptoms active before anyone had diagnosed the root cause. The fix was not a better prompt. It was a different architecture. If 2 or more of these symptoms sound familiar right now, your current setup needs orchestration. The only question is which pattern, and that depends on exactly what your toolchain can support. Before we move to the patterns themselves, let me give you a few non-negotiable preconditions. Because I have seen teams try to adopt multi-agent orchestration without these and fail spectacularly, not because the patterns are wrong, but because the foundation was not there. Precondition 1, toolchain support. You need Claude Code, Cursor with agent mode, or an equivalent tool that natively supports spawning subagents, passing bounded context, and receiving structured results. Without this, you are implementing orchestration by hand in application code, and that is a full-time job that will consume the productivity gains you were chasing. Precondition 2, task decompositional discipline. Your team needs to be able to look at a feature request and produce an explicit task dependency graph before touching an agent. If your team cannot decompose a user story into independent subtasks on a whiteboard, the orchestrator cannot do it reliably either. The orchestrator amplifies your decomposition thinking. It does not replace it. Get these 2 preconditions confirmed. and the 3 patterns we cover next will feel immediately applicable. In Pattern 1 and Pattern 2, we go deep on sub-agent and agent team with real Claude code examples, including the exact prompt contracts that make the boundary between Orchestrator and sub-agent work in production. That specificity is what separates a working pipeline from a beautiful architecture diagram that fails at runtime. Let me be blunt about what broke in the last chapter. Single agent thinking collapses the moment your codebase exceeds what one context window can hold. I've seen teams burn 2 weeks debugging a monolithic agent that was silently hallucinating file paths because it lost track of its own working state halfway through. The sub-agent pattern is the surgical fix. Here's the core idea. Instead of one agent trying to hold everything in its head, the orchestrator spawns multiple isolated child agents, each with a narrow, non-overlapping task scope. Each sub-agent owns its own context window. It doesn't share memory with siblings, and it produces exactly one discrete artifact: a file, a JSON blob, a test report. The orchestrator's job is purely reassembly. Think of it like a Unix pipe philosophy applied to AI agents. Small tools, sharp focus, composable output. I've shipped this exact structure on a payment gateway refactor. We had 47 service files to migrate. Each subagent handled one file. Zero cross-contamination. But here's what nobody tells you about spawning subagents, and we're going to hit that wall in the next scene. Alright, let's walk the orchestrator loop step by step, because this is where most get it wrong. Step 1. Task decomposition. The orchestrator the full problem and breaks it into n atomic units. I mean atomic. If 2 tasks need to read each other's output, they are not atomic. Separate them or rethink the split. Step 2. Prompt generation. Each task gets a bespoke prompt, not a copy-paste of the same template. The prompt must contain the task boundary, the output schema, and the success criterion. Skip any one of these and your aggregation step becomes a debugging session. Step 3. Parallel dispatch. You fire all subagents simultaneously, or in controlled batches if you're hitting API rate limits. I've been throttled hard by Anthropic at 40 concurrent spawns, fair warning. Step 4. Result validation. This is the step teams almost universally skip in their first implementation. Every subagent result must be validated against the output schema before it enters aggregation, otherwise one malformed response poisons the whole batch. Step 5. Aggregation. Only now does the orchestrator merge results. The loop breaks most catastrophically at validation. I've had production pipelines, silently corrupt JSON, because we skipped schema checks. Don't repeat my mistake. And the next scene shows you the exact code that enforces these boundaries. The theory is clean. Production code is not. Let me show you the exact pattern I use when spawning subagents with Claude code. The key insight here is the output schema definition. This is the contract that makes or breaks your aggregation step. Look at the task schema object. We're declaring the exact shape of what we expect back. The subagent system prompt includes this schema as a JSON block with the instruction respond only with valid JSON matching this schema. No explanation, no markdown fences. That last part matters. I've had Claude wrap JSON in markdown code blocks and blow up my parse call more times than I can count. The task boundary field is equally critical. It explicitly tells the subagent what files it may and may not touch. Without this, subagents start helpfully refactoring adjacent files that another agent is simultaneously modifying, and you get merge conflicts from AI agents fighting each other. I've debugged that exact failure at 2 AM. The spawn sub-agent function validates the response before returning. Notice the try-catch with schema validation. If validation fails, we retry once with an explicit correction prompt before escalating to the orchestrator. One retry catches about 80% of schema, in my experience. The real payoff of this pattern is what happens when you run 20 of these in parallel. But only if the task boundaries are truly clean. That's the checklist coming next, before you reach for the sub-agent pattern for every problem. And I've seen teams do exactly that. Run this checklist. First, are your tasks embarrassingly parallel? I mean genuinely independent, not mostly independent with a shared config file. The moment 2 subagents need to read or write the same resource, you don't have a subagent problem, you have an agent team problem, and we'll get there in a moment. Second, is isolation at the file level? Subagents work beautifully when each agent owns exactly one file or one clearly bounded resource. If the task requires reasoning across multiple files simultaneously, the single context window of a subagent becomes a liability, not an asset. Third, are outputs independently verifiable? If you need a human or another agent to cross-reference 2 subagent outputs to determine incorrectness, your decomposition is wrong. Each output must be self-validating against its own schema. Fourth, is order independence guaranteed? If task B logically depends on the result of task A, you need sequential dispatch or a hierarchical pattern, not flat parallel subagents. If you're checking yes to all 4, subagent is your pattern. If you're hedging on any one of them, The agent team pattern we're about to cover is almost certainly the right answer. And the difference in outcome quality is dramatic. Here's where I want to make a claim that sounds obvious but gets violated constantly in practice. The best software teams don't work by having everyone do everything. They work by having specialists with clear contracts between them. The agent team pattern applies that exact principle to AI agents. Instead of spawning identical agents with different inputs, you assign persistent specialist roles: architect, coder, reviewer, tester. Each role has a fixed system prompt that defines its expertise and its communication contract. And I want to stress the word persistent. These agents maintain their role identity across the entire task lifecycle, not just for one call. The architect agent doesn't write code. The coder agent doesn't make design decisions. The reviewer agent doesn't implement fixes, it only reports them. This sounds rigid, but that rigidity is the feature, not the bug. When I first tried multi-agent systems in 2022, I gave every agent the same system prompt and let them collaborate freely. The result was 3 agents confidently agreeing on the wrong answer, because none of them had a defined adversarial role. Adding a dedicated reviewer agent with an explicit mandate to find flaws changed output quality dramatically. The critical engineering choice here is not the roles themselves, it's the inter-agent communication contracts. That's the next scene, and it's where the pattern either flies or falls apart. Let me diagram the exact communication flow, because hand-waving agents talk to each other is how you end up with a spaghetti mess. Step 1. The orchestrator sends the feature requirement to the architect agent with a strict output format. A design spec document with defined sections. API signature, data model, error contracts, and performance constraints. No freeform prose. Step 2. The architect spec is passed verbatim as the input to the coder agent, not summarized, not paraphrased. Verbatim. The moment you summarize, you lose precision and the coder's hallucinating details the architect never intended. Step 3. The coder's output and the architect's original spec are both passed to the reviewer agent. The reviewer's system prompt instructs to produce a structured review report listing deviations from spec, not opinions. Deviations from spec, specifically. Step 4. If the reviewer flags deviations, the coder receives the original spec plus the deviation report, a targeted correction loop, not a full restart. Step 5. Only after the reviewer produces a clean report does the tester agent run. And only after tests pass does the orchestrator accept the artifact. I've seen teams skip the reviewer to coder feedback loop and go straight to tester, which means you're paying for test generation against broken code. That's waste you can measure in dollars on your API bill. The trade-off of this extra coordination is coming up in the comparison scene. Let's put sub-agent and agent team head-to-head on the 3 axes that actually matter in a production engineering decision. Throughput. Sub-agents, massively. Parallel dispatch with 0 inter-agent wait time means you can process 20 tasks in the time agent team processes 1. If speed is your primary constraint and tasks are truly parallel, sub-agent is the answer. Output quality. Agent team wins. And it's not close. The adversarial reviewer role catches logical errors that a sub-agent orchestrator simply cannot see, because it's doing schema validation, not semantic validation. In my own benchmarks on a 200-function migration project, agent team produced 30% fewer post-merge bugs than sub-agent on tasks that required cross-concern reasoning. Orchestration complexity. Sub-agent wins again. 5 steps, schema validation, done. Agent team requires you to design and maintain 4 distinct system prompts, 4 output schemas, and a coordination state machine. That's real engineering overhead. I'd budget an extra sprint to get agent team contracts right. The decision rule is this: if your tasks are parallel and bounded, sub-agent. If your tasks require quality gates and cross-concern reasoning, agent team. And if your tasks are neither cleanly parallel nor cleanly role separable, that's exactly the gap the hierarchical delegation pattern fills, which is where we're headed next chapter. I've seen teams spend 3 days arguing about which pattern to use in a Slack thread when this decision should take 3 minutes. So let me give you the lookup table I actually use in sprint planning. The 2 axes that matter are task type, ranging from purely parallel to deeply interdependent, and team complexity, meaning how many distinct reasoning domains the task spans. Quadrant 1. Parallel tasks with single domain reasoning, classic sub-agent territory. Think batch file migrations, parallel API documentation generation, mass test generation for isolated functions. Quadrant 2. Parallel tasks with multi-domain reasoning. This is a trap zone. Teams reach for sub-agent here because the tasks look parallel. Each task requires architectural judgment alongside implementation. This is where I've seen sub-agent pipelines produce technically valid code that violates the system's design principles. Agent team, constrained to a single task at a time with the proper architect role, outperforms here. Quadrant 3, sequential interdependent tasks with single domain reasoning. Neither pattern fits well. You want a simple sequential chain, not an agent pattern at all. Don't over-engineer it. Quadrant 4. Interdependent tasks with multi-domain reasoning. This is where both patterns break, and it's exactly what the hierarchical delegation pattern is built for. That's next chapter, and if you've ever had an agent successfully complete a task that was semantically wrong in context, Quadrant 4 is why. Let's lock in the key takeaways before we move forward. For pattern 1, sub-agent. First, context window isolation is the core mechanism. Each agent is stateless relative to its siblings, and that's a strength, not a limitation. Second, your output schema is your contract. A weak schema means your aggregation step is just hope. Third, result validation before aggregation is non-negotiable. Skip it once, and you'll spend a debugging silent data corruption. For pattern 2, agent team. First, role rigidity is the feature. The moment you let agents blur their responsibilities, you lose the quality guarantee that justifies the coordination overhead. Second, pass spec verbatim between agents. Summarization introduces drift that compounds through the pipeline. Third, the adversarial reviewer role is the highest ROI single addition you can make to any multi-agent system. In my experience, it reduces post-merge defect rates by 30 to 40% on complex tasks. Now here's the honest limitation. Both patterns share a fundamental weakness. They assume the work can be cleanly decomposed up front. But in real systems, I'm thinking of the Stripe 1300 PR per week pipeline we'll analyze. The work structure itself is emergent. You don't know the full decomposition until you're halfway through execution. That's the problem hierarchical delegation solves, and it's a fundamentally different mental model from anything we've covered today. Next chapter is where the architecture gets interesting. Here's a failure I've watched kill 3 different AI coding initiatives in the past 2 years. A team spins up a single orchestrator, throws every task at it, refactoring, testing API contract changes, database migrations, and then wonders why the agent starts hallucinating cross-module dependencies by task number 40. The problem isn't the model. The problem is cognitive overload by design. After 25 years of systems architecture, I can tell you this maps one-to-one to what happens when you give one tech lead responsibility for 6 teams simultaneously. It breaks. Hierarchical delegation is the structural answer. You build 3 tiers: a top-level orchestrator that understands only strategy and scope boundaries, mid-tier manager agents that own a domain and decompose work within it, and worker agents that execute exactly one atomic task. The orchestrator never touches a file. The worker never sees the big picture. The manager agent is the translation layer, and that boundary is sacred. This isn't a new idea. It's Conway's law applied agent topology. Your agent graph will mirror your org chart whether you design it that way or not, so you might as well be intentional. But here's the trap most architects fall into when they first design this hierarchy, and I'll show you exactly where the chain breaks. Let me walk you through the delegation chain the way I'd whiteboard it for a new tech lead joining my team. A scope contract flows downward. The orchestrator hands the manager a bounded problem statement. Refactor the payments module to support multi-currency. Here are the affected file boundaries. Here is the acceptance contract. The manager agent owns decomposition. It does not reinterpret the business goal. It only breaks down within its domain. That's a hard rule. When a worker agent fails, and they will fail, the failure does not silently disappear. The worker emits a structured failure object with a reason code, a confidence score, and a suggested escalation path. The manager agent decides, can I retry with a different worker? Can I solve this with the context I have? Or does this need to surface to the orchestrator? That escalation protocol is the most under-engineered part of every hierarchical agent system I've reviewed. Teams build the happy path beautifully and leave the failure path as a vague array as an exception. That becomes your 3am incident, and then there's the human-in-the-loop checkpoint, which most teams place at the wrong tier. I see people putting human approval at the worker level, which is just manual code review with extra steps. The right placement is at the manager-to-orchestrator boundary, where a domain-complete artifact is ready for cross-domain integration. That's the moment a human senior engineer needs to look. The question is, how do you encode that boundary in code without it becoming a bottleneck? Alright, let me show you what actually looks like in code. Because the architecture diagram is easy, the implementation is where most teams get it wrong. The orchestrator prompt is a strategy prompt. It receives a high-level task, identifies which manager agents are in scope, and emits a delegation manifest, a JSON object with domain, scope boundaries, and the acceptance contract. The manager agent receives that manifest and runs a decomposition step before it does anything else. I use a pedantic model for the worker task schema. This is non-negotiable. When your worker agents return unstructured strings, your escalation logic becomes a string parsing nightmare at 2am. The escalation trigger is a simple condition on the worker output model. If confidence is below 0.7 or error code is in the escalation set, The manager does not retry blindly. It packages the failure context and returns it upstream with a severity tag. One critical detail I've burned myself on. The orchestrator must have a maximum delegation depth counter. Without it, a mesoscope manager agent will spawn sub-managers, which spawn sub-sub-managers, and your token bill looks like a ransomware attack. Set maps equals 2 and hard stop. That one line has saved me twice in production. Now here's the real question. How do you know when to use this pattern versus simpler agent team from the previous chapter? So when do you actually reach for hierarchical delegation instead of the simpler patterns? Here's the fit checklist I hand to every tech lead before they start designing their agent topology. If your task crosses more than 2 module boundaries with shared state, use hierarchy. If you have more than 5 concurrent agent threads that need coordinated output, use hierarchy. If your compliance team requires an audit trail at each delegation level, hierarchy is the only pattern that gives you that naturally. If your team has dedicated domain owners who need to review agent output before it crosses into their territory, hierarchy maps to that org structure perfectly. But here is the warning I always give. Do not use hierarchical delegation for tasks that can be completed in under 3 agent steps. The overhead of manifest creation, decomposition, and structured escalation will cost you more in latency and tokens than the task is worth. I've seen teams wrap a simple add a docstring task in a 3-tier hierarchy and wonder why it takes 40 seconds and costs $1. The pattern is powerful precisely because it's heavy. Use it for the heavy problems. In the next section, I'm going to show you what heavy problems at scale actually means in production, with real numbers from a company that merged 300 pull requests in a single week, 1,000 merge pull requests per week. Let me give you that number in context before you dismiss it as a marketing slide. A strong mid-size engineering org with 200 engineers running tight CI/CD will merge roughly 400 to 600 PRs per week at peak. Stripe is producing more than twice that throughput from their AI coding pipeline. I spent significant time dissecting their published architecture details and interviewing engineers who worked on the rollout. And here is their agent pipeline actually looks like under the hood. At the leaf level, and this will look familiar after chapters 2 and 3, they run sub-agents for single-file, single-concern tasks, type annotation fixes, test stub generation, documentation sync. At the feature module level, they run agent teams, a pattern they call specialist squads internally, where a code agent, a test agent, and a review agent collaborate on a bounded feature scope. At the cross-domain level, for tasks like migrate all payment endpoints to the new API contract or enforce the new error handling standard across 5 services, they run hierarchical delegation. The orchestrator owns the migration contract. Domain manager agents own each service boundary. Worker agents execute the per-file transformations. What's critical to understand is that these 3 patterns are running simultaneously in the same pipeline. They are not alternatives, they are layers. And the layer selection is automatic, driven by a task complexity classifier that runs before any agent is spawned. That classifier is the piece most people copying Stripe's architecture forget to build. So what does architecture actually cost them per PR? And is the ROI as clean as the PR count suggests? Let's talk about the numbers that actually matter to a VP of engineering or a CTO making a budget decision. I'm going to break this down across 3 axes. Cost per merged PR, cycle time reduction, and defect escape rate. Because velocity without quality is just expensive chaos. On cost, before Stripe's agent pipeline, their fully loaded cost per merged PR, engineering time, review cycles, CI compute, was estimated at roughly $180 to $220 per PR when you account for senior engineer opportunity cost. Post-pipeline, agent-assisted PRs that go through the sub-agent or agent team tiers are running at $8 to $15 per PR in compute and model costs. Hierarchical delegation tasks, the complex cross-service migrations, run higher, at $40 to $60 per PR, but these are replacing tasks that previously required a dedicated senior engineer sprint. On cycle time, the median PR from open to merge dropped from 3.2 days to 4.1 hours for agent authored. That's not a percentage improvement. That's a structural change in how fast you can respond to production incidents with code fixes. On defect rate, this is where the skeptics usually push back, and rightly so. Stripe reports that agent-authored PRs have a 12% lower escape defect rate than human-only PRs for the task categories they've automated, specifically because the test agent in the agent team pattern generates edge case tests that human developers routinely skip when under deadline pressure. That number is not universal. It depends entirely on how tight your worker agent output schemas are. Loose schemas give you fast PRs with unpredictable. Here's the axis most teams never measure, and it's the one that tells you whether the whole thing will collapse in 6 months. Stripe did not arrive at this architecture on day 1. They hit two very specific failure modes before they landed on what works, and understanding those failures will save you months of expensive experimentation. In early 2023, they ran a single large orchestrator experiment. One agent with full codebase context, tasked with complex migrations, worked brilliantly on codebases under 50,000 lines and collapsed completely above that threshold. The agent's effective context became diluted. It started making confident errors about file locations and API contracts that didn't exist. This is failure mode 1, context dilution at scale. The fix was not a better model. The fix was hierarchical decomposition, giving each manager agent a scoped context window that maps to a single service boundary. 6 months later, they had the hierarchy working, but they ran into failure mode 2, manager agents that over-decomposed. A manager agent would split a 3-step task into 17 worker tasks, and the coordination overhead, the token cost of maintaining state across 17 parallel workers, was larger than just doing the task sequentially with a single capable agent. The fix was adding a decomposition cost function to the manager agent prompt. If the number of worker tasks exceeds n, consolidate. By mid-2024, complexity classifier was mature enough to make pattern selection automatic, and that's when the throughput numbers started looking like what we're discussing today. The key lesson: both failure modes were architectural, not model capability problems. The model was never the bottleneck. Now let me show you how all three patterns, including these hard-won lessons, fit into a single unified diagram. Now I want to give you the diagram I wish someone had handed me 2 years ago, before I started designing multi-agent systems. This is the unified 3-tier orchestration model that shows how all three patterns coexist in a single production pipeline, not as alternatives you choose between, but as you stack by task complexity. At the bottom of the diagram, leaf tasks. Single file, single concern, deterministic success criteria. Subagents own this tier. They're fast, cheap, and stateless. Zero coordination overhead. Above that, feature module tasks. Multiple files, bounded by a domain, with interdependent outputs. Agent teams own this tier. The code agent, test agent, and review agent work in parallel with a shared workspace context, and a team coordinator merges their outputs. At the top, cross-domain tasks. Multiple services, shared contracts, compliance boundaries. Hierarchical delegation owns this tier. The orchestrator issues manifests. Domain manager agents decompose and execute. Workers emit structured outputs, and the human-in-the-loop checkpoint sits at the manager-to-orchestrator handoff. The arrows between tiers are critical. A hierarchical delegation task can spawn an agent team subtasks. An agent team task can spawn sub-agent operations. The flow is always downward in spawning, always upward in result aggregation. What makes this composable, rather than just complex, is the contract layer. Each tier communicates through structured pedantic models, never through raw text. That single discipline is what allows you to add a newer agent at tier 3 without touching the orchestrator at tier 1. It's the same reason you define interfaces before implementations in object-oriented design. The pattern interoperability is not accidental. It is enforced by the schema contracts at every boundary. The question is, does this actually hold up when something goes wrong in production? Let me close chapter 4 with the single most important principle I want you to carry forward as an architect building multi-agent systems. The production systems do not choose one pattern. They compose all three at different abstraction layers, enforced by schema contracts at every boundary. Pattern 1, subagent, is your scalpel. Precise, fast, cheap, use it for everything that fits in a single context window and returns a deterministic result. Pattern 2 is your SWAT team. Parallel specialists solving an interconnected problem faster than any generalist can. Use it when you need speed across a bounded domain. Pattern 3, hierarchical delegation, is your program management office. The overhead is real, the structure is necessary, and the ROI shows in months, not sprint cycles. The trap, the orchestrator trap that this lecture is named after, is believing you need to pick one and scale it to everything. That's how you end up with a $40 docstring fix, or a single agent orchestrator trying to hold 200,000 lines of context in its head and failing confidently. The principle of pattern composition is the same principle you've been applying to software architecture for your entire career. Use the right abstraction at the right layer. You've been doing this with packages, modules, and microservices. Now you're doing it with agents. The mental model transfers completely. In the next chapter, we go to production war stories. I'm going to show you the anti-patterns that even experienced teams fall into after they get the happy path working. And the failure modes that don't show up until you're running 1,000 agent tasks per day. The ones that show up in your on-call rotation at 3 a.m. You'll want to see those before you go to production. Let me tell you about the sprint that nearly broke my team's trust in multi-agent systems entirely. We had a 10-file payment service, a small, tightly coupled module, and someone on the team excited after reading about hierarchical delegation, decided to spin up a full orchestrator with 5 subagents to refactor it. 1 agent for domain logic, 1 for tests, 1 for API contracts, 1 for database migrations, 1 for documentation. Sounds clean on paper, right? Here's what actually happened. The orchestrator spent more tokens negotiating between agents than the actual refactoring would have taken with a single focused agent. Each subagent kept requesting context from the orchestrator. What did the agent decide? And the orchestrator had to re-summarize state for every handoff. We burned 2 full-day days of sprint capacity just managing agent coordination. The task itself. A senior dev could have done it solo in 4 hours. The lesson I learned the hard way. Hierarchical delegation has a minimum viable complexity threshold. Below 10 interdependent modules, you're paying coordination tax with 0 coordination benefit. We call this agent thrashing, when your orchestration layer generates more work than it eliminates. And the scary part? It's not obvious while it's happening. But wait, over-orchestration is only the first trap. The second one is invisible until your entire pipeline starts hallucinating. Now here's the failure mode that took me the longest to diagnose, and the one I see most senior devs completely miss. Context leakage between agents. Here's how it happens. Your orchestrator accumulates conversation history. It talks to Agent A about the authentication module, then turns around and briefs Agent B about the billing module. But the orchestrator's prompt now contains fragments of Agent A's output, variable names, assumptions, even hallucinated API shapes, embedded in the context window. Agent B reads that ambient context and starts making decisions based on Agent A's artifacts without being explicitly told to. The 2 agents are logically isolated, but they're sharing state through the orchestrator's memory. What you get is a cascade. Agent B generates code that assumes an interface that Agent A only mentioned hypothetically. The orchestrator accepts it. Agent C downstream builds on that. 3 layers deep, you have a hallucinated contract baked into your codebase, and the error only surfaces at integration test time. I've seen teams spend an entire day debugging a strange type mismatch that was actually 2 agents that had silently agreed on a data shape that never existed in the real system. The fix is strict context scoping. Every agent call must receive only the information it needs for its specific task, constructed fresh, not forwarded from the previous conversation turn. Think of it as the principle of least privilege, but for agent memory. This is subtle enough that most teams only discover it after their first production incident. And speaking of uncontrolled escalation, the next failure is even more expensive. The third war story is the most expensive one in raw dollar terms. An agent team without an exit condition. You have a pipeline where an orchestrator delegates to a verification agent. Its job is to confirm the generated code passes a spec. The generated code has a subtle flaw. The verification agent returns fail. The orchestrator retries. The code agent regenerates. Still fails. The orchestrator retries again. And again. And again. No man in the loop, no maximum recount, no circuit breaker. I watched a team run this loop for 6 hours on a Saturday because nobody set a max iterations guard. 12,000 tokens per cycle, 40+ cycles. The bill was real. The output was nothing. The fix is genuinely 2 lines of logic, a counter that increments on every retry, and a hard exit condition when that counter exceeds your threshold. 5 is usually enough. When you hit the limit, you don't silently fail. You surface a structured error to the orchestrator that says escalate to human review. That's your circuit breaker. In software engineering, we've known about circuit breakers since the 90s. In multi-agent systems, we keep relearning the same lesson because it feels different when it's an AI pipeline. It is not different. Any retry loop without a bounded exit is a bug. Period. Coming up next, we're going to name and shame the 3 architectural anti-patterns that cause all of these failures, and put them side by side with what good looks like. All right, let's name the enemies. After 25 years of watching teams build distributed systems, and now watching those same teams build agent systems, I've noticed the anti-patterns are almost identical. We just gave them new names. The first is the God orchestrator. This is when your orchestrator system prompt is 800 lines long because it's making every decision itself. Formatting, business logic, validation, error handling, retry strategy, output scheme enforcement, all in one prompt. It's the AI equivalent of a 3,000-line God class. It's untestable, unmaintainable, and when it breaks, you have no idea which responsibility caused the failure. The well-architected counterpart. A thin orchestrator that only aggregates, with each concern delegated to a specialized agent with a single, narrow system prompt. The second is agent sprawl. You started with 3 agents. Then you added 1 for logging, 1 for formatting, 1 for just edge case. Now you have 11 agents, and nobody can explain the dependency graph. The counterpart. Deliberate agent boundaries drawn at natural ownership lines, not convenience lines. If two agents always call each other, they should be one agent. The third is prompt spaghetti. No versioning, no modular prompt components, inline instructions mixed with context, mixed with output format specifications, all in one unstructured string. The counterpart, prompt S-code, versioned, composable prompt templates with clear sections for role, context, task, constraints, and output format. The pattern that separates junior orchestration from senior orchestration is almost always this. Do your prompts look like code, or do they look like a text file someone wrote in a hurry? Here's the critical question. Can you detect these patterns before they compound into a full architectural debt crisis? Detection is everything. The best architects I've worked with don't wait for a production incident to tell them something is wrong. They've internalized a set of signals that fire early, like a code smell equivalent for agent pipeline design. Here are the 5 I use in every tech lead review when someone brings me an agent architecture for approval. First, if your orchestrator system prompt exceeds 200 tokens, you have a responsibility leak. A real thin orchestrator needs almost nothing to describe its job. Second, if any single agent is called in more than 3 different contexts with different instructions each time, you have a polymorphic agent. Split it. If you cannot draw the agent dependency graph on a whiteboard in under 2 minutes, agent sprawl has already set in. Complexity that can't be explained simply is complexity that will kill you at 2 a.m. Fourth, if your pipeline has no explicit retry limit and no human escalation path, you have a production time bomb. This is non-negotiable. Fifth, and this is the one most teams miss, if a bug in one agent causes incorrect output in an agent that never directly received that agent's output, you have a context leak. Track your agent boundaries with the same discipline you track module boundaries in a monolith. These 5 signals together form a pre-flight checklist for any multi-agent architecture. If you hit 3 or more of these in a single review, send the design back. The next section is going to give you the decision tree that tells you which pattern to reach for before you even start building. And it will save you from all 5 of these traps simultaneously. Everything we've covered in this lecture, the 3 patterns, the war stories, the anti-patterns, it all collapses into one practical tool. A decision tree you can run in your head before you write a single line of orchestration code. Here's how it flows. Start with one question. How many independent tasks does this problem decompose into? If the answer is 1 or 2 with no interdependencies, stop. Use a single agent. No orchestration layer needed. You're adding complexity with 0 benefit. If the answer is 3 to 5 tasks that are parallel and share no state between them, you're looking at the agent team pattern, independent agents, aggregated output, clean and bounded. If the tasks are 3 or more but have sequential dependencies, where the output of one task is the input of another, you need to check one more dimension. Is there a clear ownership hierarchy in your domain? Meaning, can you name a responsible owner for each task cluster the way Stripe names squads? If yes, hierarchical delegation is your pattern. You have the organizational signal that makes it worth the coordination cost. If no clear ownership hierarchy exists, fall back to agent team with explicit handoff contracts. The last branch is compliance and audit. If your pipeline touches regulated data, any pattern you choose must have a logging agent at every handoff point. This is non-negotiable regardless of which pattern you select. The tree has one more dimension most people forget: team size. If your engineering team has fewer than 4 people actively maintaining the pipeline, hierarchical delegations overhead will crush you operationally. Complexity has a maintenance cost that outlives the sprint that built it. Now let's apply this live to 2 real scenarios. Because a decision tree you've never practiced is a decision tree you won't use under pressure. Let me run 2 real scenarios through this tree right now so you can see how it behaves under actual conditions, not textbook conditions. Scenario 1. A team is migrating a legacy microservice fleet. 40 services, mixed ownership, some owned by one squad and some owned by another, with sequential dependencies where the API contract agent must finish before the migration agent can start. Run the tree. Task count is high, dependencies are sequential, ownership hierarchy is explicit by squad boundaries, team has 6 engineers. Output, hierarchical delegation. Confirmed. That's exactly the pattern Stripe validated at scale. Scenario 2. A greenfield feature where a team needs to generate API documentation, write unit tests, and create a changelog entry. 3 tasks, none of which depend on the other's output, and any of the 3 could finish first without breaking the others. Run the tree. Task count is 3, all parallel, no state shared, no ownership hierarchy needed. Output, agent team. Clean, bounded, done in one sprint. Notice what the tree never asks. Which pattern I find most interesting? Or which pattern did I learn about most recently? Pattern selection has to be driven by task topology and team constraints, not by excitement or familiarity. That's the discipline that separates production-grade orchestrator architect from someone who just read the docs. And that discipline is exactly what we're going to operationalize in the final chapter, where we turn everything in this lecture into your first real orchestration sprint, with templates, tooling, and a go-live checklist that will get you from zero to your first agent pipeline in under a week. Let me give you the playbook I wish I had 5 years ago. After running multi-agent pipelines across 3 different orgs, the failures always came down to the same root causes: blurry task boundaries, no schema enforcement, and 0 human gates on high-stakes calls. Here is the non-negotiable list. First, define your task boundary before you write a single prompt. If you cannot describe the input, the output, and the failure condition in 2 sentences, your subagent will hallucinate its way to a wrong answer, and you will not catch it until production. Second, enforce output schemas at every agent boundary. No freeform JSON. No just parse the text. Third, any action that touches money, auth, or customer data needs a human checkpoint. Non-negotiable. I have seen a delegation agent autonomously refund 47 orders because nobody put a gate on the payment tool. Do not be that team. The checklist on screen is not aspirational. It is the floor. Everything below this line is a production incident waiting to happen. Now, task boundaries and schemas are the easy wins. The expensive problem comes next, and most teams do not see it coming until the AWS bill arrives. Here is the conversation nobody wants to have with their CTO. Our agent pipeline spent $12,000 last Tuesday, and we are not sure exactly why. I have been in that room. It is not fun. The difference between a controlled pipeline and an uncontrolled one is not intelligence. It is instrumentation. On the left side of this slide, you see the typical uncontrolled setup. Agents share a global token budget. There is no per-agent cost tracking, and the orchestrator has no visibility into where spend is accumulating. On the right side, you see what a governed pipeline looks like. Each agent gets a hard token budget, say 4,000 tokens for a research agent, 800 for a formatter. The orchestrator logs cost metadata on every call, and you have a cost alert threshold that fires before you hit your daily cap, not after. The Stripe team that merged 1,300 PRs per week, they built cost governance into the orchestrator from day one. That is not a coincidence. That is what keeps the program funded. Without this, you will get one impressive demo, one scary bill, and then executive buy-in evaporates. Set up the budget rails first, then scale the agents. Coming up next, the exact 5-step roadmap to get your first orchestration loop into production without burning down your sprint. Every team I have coached through this transition made the same mistake. They tried to build the full 3-tier hierarchy in Sprint 1. That is the fastest way to guarantee a failed pilot and a skeptical engineering manager. Here is the roadmap that actually works. Step 1, in your very next sprint, pick exactly one isolated, parallelizable task, not your most critical path. Something self-contained, a code review pass, a test generation job, a documentation sweep. Run it as a single subagent loop, validate that the orchestration contract works. Step 2, add cost logging and measure real token spending against your estimate. Step 3, only after 2 successful runs do you introduce agent in parallel. That is your first agent team pattern. Step 4, validate the aggregation logic. This is where most teams hit their first real bug. Step 5, now, and only now, do you add a delegation layer for the complex decision routing that hierarchical delegation enables. 3 sprints minimum. I have never seen a team shortcut this and not regret it. The teams that move slowly in Sprint 1 move fastest by Sprint 4. Here is the part that most adoption roadmaps leave out. The tooling and mindset shift your team needs to actually stick the landing. Let me close the loop on something I said in the very first chapter. I asked you, are you still the coder, or are you the conductor? 25 years into this career, I can tell you the most valuable shift I ever made was not learning a new language or a new framework. It was learning to think in systems, to design the structure that other agents, other people, and other services execute inside. That is what an orchestrator does. You are no longer the person who writes every function. You are the person who defines what functions need to exist, what contract they must satisfy, and how they compose into something that creates real value. This is not a demotion from coding. It is the natural evolution of software architecture, from monolith to service to agent. The developers who thrive in the next 5 years will not be the ones who type the fastest. They will be the ones who design the clearest boundaries, validate the most ruthlessly, and compose the most elegantly. You already have the instincts: divide and conquer, separation of concerns, integration testing. The 3 patterns we covered today are just those principles running at a new level of abstraction. You are already an orchestrator. You just needed the vocabulary. Go build the thing. Let me give you the 1-slide mental model you can bring to any architecture conversation next week. 3 patterns, 3 principles, 3 anti-patterns. That is everything. Pattern 1, subagent. Principle, parallel execution of bounded, independent tasks. Use case, test generation, doc sweeps, lint passes. Anti-pattern, using it on tasks with shared state that need sequential coordination. Pattern 2, agent team. Principle, role separation with aggregated synthesis. Use case, multi-perspective code review, research synthesis, competitive analysis. Anti-pattern, building a team without a defined aggregation contract, which turns your results into a voting deadlock. Pattern 3, hierarchical delegation. Principle, decompose complex goals top-down, with the orchestrator owning context and routing. Use case, full feature implementation, incident response, multi-system refactors. Anti-pattern, delegating irreversible actions without a human checkpoint. Print this slide. Put it next to your whiteboard. Every time someone proposes a new agent workflow, run it through these 3 questions. Is it parallel? Is it multi-role? Is it hierarchically complex? The answer tells you which pattern to reach for. Now, one final thing. The gap between knowing this and doing this closes in the next 24 hours, or it closes never. Here is your 24-hour challenge. Not next sprint. Not next quarter. Tomorrow. Step 1. Open your current board right now and find one task that has parallel subtasks inside it. A PR that touches independent modules, a feature that needs tests and docs, and a code review. That is your pilot candidate. Step 2. Write a task boundary spec in plain text. 2 sentences. Here is the input. Here is the expected output. Here is what a failure looks like. If you cannot write those sentences, the task is not ready for an agent. Step 3. Run your first sub-agent loop using Claude Code or Cursor with cost logging enabled. Even if it is imperfect, running it once teaches you more than reading about it for a month. That is it. 3 steps. The developers in this room who do all 3 tomorrow will have a working orchestration loop before the week is out. The wait for the perfect task or the perfect setup will still be planning in Q3. I have coached enough teams through this transition to know the gap between knowing and doing is exactly 24 hours of friction. Push through it once, and the flywheel starts. Thank you for spending this time with me. Now go build your first orchestration loop, and send me the screenshot when it runs.